is filled with confidence intervals and hypothesis tests, but it's going to be where the population standard deviation is not known. And so we calculate it from the sample that we take, just like we calculate the sample mean. And when we do that, we have a different distribution. We have what is called the t distribution. And so we're going to have that distribution in this chapter. So we'll be looking at conditions for inference about a mean, the t distributions, the one sample t confidence interval, and then the one sample t-test. There's examples of technology that I've removed because we're not actually using that in this course. So you'll see that in the textbook, though. There's lots of Excel. You can ignore it, or you can, if you want to use it as supplemental material, you can. We're also, though, going to look at matched pairs and the robustness of the t procedures, how reliable they are. So we will get started. So the conditions, very similar to what we've been doing. We have a simple random sample. We're assuming we are taking a sample from the population, right? That's always step one. We're taking a sample from the population, and then we want to use it to draw conclusions about the population. It's very important that it is a simple random sample. Observations from the population also have a normal distribution, right? With mean mu and standard deviation sigma. So in practice, it is enough that the distribution be symmetric and single peaked. So if it's symmetric and single peaked like that, it's fine, unless the sample is really, really small. Both mu and sigma, so these are the population mean and the population standard deviation. In this chapter, both are unknown, where previously only just the mean was unknown. We were trying to estimate the mean. Here we are estimating the mean as well, but we're doing it with an unknown standard deviation. And so how do we do that? How can we do that? So just the conditions continue on this page here, on this slide as well. So we need to make sure that the population is large, say at least 20 times as large. If it isn't, then the theorems and the estimates don't hold. So it needs to be a sample from a fairly large population. And like I just said, previously we assumed what the population standard deviation was. It was given to us in the scenario. It's usually based on previous studies, but what if there were no previous studies and we have no idea? So how can we determine what sigma is? So we will estimate it with S. Do you remember S from way back in chapter 2? Right? Remember how we calculated S? It was the standard square root of each value, subtract its mean squared, divide by n minus 1. It's called the sample standard deviation, right? And so when you get your sample from the population, you calculate the mean, and you also will calculate the standard deviation. For our purposes, we speed up that process and we give you those values because we just say, hey, they've already been calculated, here's what they are. So you can just continue on and construct the confidence interval or conduct the hypothesis test. So that's the main thing for this chapter is we are estimating the standard deviation with S, the sample standard deviation. And so the standard error changes. Instead of sigma divided by square root n, the standard error ends up being S divided by the square root of n instead of sigma divided by the square root of n. And that also will change our test statistic. if you remember before, what we've been doing all along is Z, the Z table. That should be recognizable. Z equals X bar, subtract mu, divide by sigma over square root n. But now we're going to use, and it has a question mark, it's going to be a T. So you can say it's T, the question mark is T. And you can see, I'm going to highlight the difference here. The difference, the only difference between the two are the standard deviations. Z, just automatically use Z if you're given the population standard deviation. Automatically use T if you're given the sample standard deviation. You need to know what they are and how to read the scenario. If it says a sample was taken and the sample was calculated, the mean and the standard deviation was calculated as this, then you know it's coming from the sample. Okay, so you have to read the questions carefully. If it says that it was calculated, if the mean and standard deviation was calculated from the sample, then automatically you have X bar and S. Okay. And the new statistic does not have a normal distribution. It's a cousin. The T distribution is, I always call it like a cousin of the normal distribution because they almost look exactly the same, but they're a little bit different. And it was found that the T works a little bit better when you don't know the population standard deviation. So it works a little bit better. It actually comes to us from Guinness Breweries from Ireland. So the chief statistician there, the head brewmaster, was doing all kinds of tests, and he realized that he was constantly rejecting the null hypothesis when he shouldn't have been, and the lab was like, but it's right, because they were testing the contents of the beer of Guinness Breweries. And then he decided, I'm just going to tweak the distribution. He had the standard normal distribution. It was already known widely, but he decided then to come up with a new distribution. And he came up with the T distribution. And there's a plaque now at Guinness Brewery saying that he came up with the T. He had to call it T. He couldn't put it after his own name because it was done like it was Guinness Brewery. So he couldn't do that. He wasn't allowed to use his own name because it was Guinness Brewery. So they just called it T. Yeah. Yeah, so it's sort of like that. We'll see it in a moment. I have uploaded the T distribution table for everyone on Brightspace. You go to it, you'll see it. So yeah, he came up with this T distribution and he thought, this is working. This is working for when we don't know the standard deviation. And he sent it to London. From Dublin, he sent it to London and told Carl Pearson, hey, here's a new distribution that I've come up with. I've figured out all the values to it based on calculus, and you might find it handy, which is actually really funny today because this T distribution is now used all around the entire world all the time. It's that critical with these tests. And it looks like this. This is the table. You should have a copy of this on Brightspace. This is what he came up with. Want to say his name's, it's Gossett, William Gossett. Yeah. And he's got a plaque in the brewery. If you go and visit the brewery and do the tour, you'll see he is now credited for having come up with this. And it's really good. It's so much more accurate. You'll notice along the bottom, here's our Z. These are our Z stars. And if you look at the column, I'm just going to shrink it down. If you look at the column that says 95%, and you go down to the Z, you're going to get the value that I've been saying memorize. So 95% confidence interval corresponds to 1.96. So it fits really well. We're going to see in a moment how to read the T's, but if it's a Z, if you're using a Z, use this row, right? So if you want a 90% confidence interval, you use 1.645. If you want a 99% confidence interval and it's Z procedure, use 2.576. But if you don't have sigma and you're estimating the population standard deviation sigma with S, that's the sample standard deviation, then we use the T values. And we pick a T value from it. We'll see how to do that in just a moment. So what we have is these n-1 degrees. So this goes into the function to get those values. We take the size of the sample n and subtract 1, and we call that the degrees of freedom. And that's just what we've always called it. It means that it can vary. It just goes, just know that it goes into the calculation, the formula that comes up with those areas under the, for those T values for the areas under the curve. Okay, so n-1 is the degrees of freedom. And then we have each T distribution varies by the degrees of freedom. So if you change the size of the sample, you're going to get a different T. Whereas Z didn't care. Z actually doesn't care what size of the sample it is, right? We just used 1.96. Whereas T, it's important. We need to know what the size of the sample is, and you subtract 1, and then we can read the value from the table. So what does the T look like? Okay, I mentioned that it is related to the normal distribution. It is one symmetric with a single peak, like that. But it has much more area in the tails. It still sums to 1, but it's been tweaked a little bit. So if we compare it, I'm just going to increase this so we can see. If you look at the black curve that's dashed, that is our regular normal table, normal distribution, the Z. So the dashed black curve is the Z. If you look at the red curve, that is a T with 1 degree of freedom. So that means the size was 2, n was 2, subtract 1 gives you 1. So that's 1 degree of freedom. The blue curve has 3 degrees of freedom. The green curve has 8 degrees of freedom. And what do you see happening as we increase the degrees of freedom? What's going on in this picture? What's going on? Yeah, Catherine. It is. It's becoming more normal. It's converging, and it does. That's how they're related. So as the degrees of freedom increases, or as the size of the sample, as you get more, as your sample is the bigger the sample, the closer you will be to a normal distribution. It ends up converging theoretically on this table. We go from 1, 2, 3, 4, 5, 6, and then at 20, at 30, it jumps to 40 degrees of freedom, 50, 60, 80, 100, then it jumps to 1,000, and Z is actually infinity. So, and that sort of matches, because if you know the population standard deviation, that's all the values, and infinity imagines all the values. So this is that line, that row will give us all of our Z critical values, Z stars. Okay. So if you're doing a 95% confidence interval, and let's say the size is, let's say we have 5, n equals 5. So that would mean the degrees of freedom equals 5 minus 1, which is going to be 4. So we would look at this row right here, 4. And if we wanted a 95% critical T value, it would be 2.776. And that's the value you would use in your confidence interval. Okay. 2.776. Okay. 4 degrees of freedom. So you need to know the size to get the value of the T. So these are T stars. So the T star on 95 would equal 2.776. I'm using a subscript and T on 95. Subscript, sometimes they'll do a comma and go, it's 95 on 4 degrees of freedom. They'll have like 2 little subscripts. The first one is the confidence level, 95. The second one is the degrees of freedom, 4. Okay. I usually just do 95. I usually just show 1. Okay, let's see another one. Let's say we have try degrees of freedom equals let's say n equals 16. Degrees of freedom then would be 15, and our T star on 95 would be, so we're going to look at 15, this row here, and it would be 2.131. And that's the value we would use for our confidence interval. All right, they all fit really well. If you notice, as we go down, as our size, if you just look at that column with the 95%, as we increase the size of our degrees of freedom, the T values get smaller and smaller and end up as Z, 1.96. You can see even at 1,000 degrees of freedom, it's 1.962, which is really close to 1.96. So those values get smaller. So what it tells us is this whole thing tells us that the smaller the sample, the larger the T value is going to be, which means the wider our confidence interval will be. Okay. And they all fit in really nice together. The whole thing fits like a nice puzzle. It's actually easier to read. It's just one sheet. It's actually a little bit easier to read than the Z table in a sense, right? Because you just pick your value and just need to know the size of the sample, and you just look at the column and get your value. Okay. I also have posted a couple of videos on how to read the T table. The first one is how to read the T table. Part 1 is for confidence intervals, and part 2 is for the hypothesis test. So in case you forget how we did this, you can just look at those videos. They've got a little bit of noise in the background. Something was coming through on the laptop or something. It's got like some sort of buzz. Anyways, hopefully you can hear it okay. If not, let me know. Okay, so we'll go back to this one. So yeah, they look very, very different until they converge to the normal. So they become steeper and steeper, and you can see that they're heavier in the tails. There's more area under the curve for the T's than with the normal. And there's the T distribution. We just used it. I've just put it in there to give you a quick glimpse of it, but you have the full sheet on Brightspace. Okay. Right, and the confidence levels go from 50 to 99.9. Right. So you have everything you need there. And we will start by constructing a T confidence interval, a 1 sample T confidence interval. So there's the formula right there. It's X bar plus or minus T star times S divided by the square root of N, where T star is the critical value for T of N minus 1, right? Remember N minus 1 degrees of freedom. Density curve with area C. So if it's a 95% confidence interval, you get the C, you get that column where it says 95, And then it will be between negative T star and T star. And this interval is exact when the population distribution is normal and is approximately correct for large N in other cases. Okay. All right, so let's do an example. I have one starting from scratch. It's using Smarties. It's like a quality control industry question, just like our ice cream from before, but this time it's with Smarties. So to speed up some time, I'm going to give you the values. So actually, no, the values are given. So I did put them in here. So I have x bar is equal to, so what would you say from this scenario? So we have 5 boxes of Smarties randomly selected, and you count the number in each box. We get 56, 61, 54, 52, and 52, 5 boxes, right? And they should be roughly the same, but some boxes will have more, some will have less. And we calculate the mean, and it is 55 Smarties. I used to do this without the mean and standard deviation, but it took quite a while to get the standard deviation. I don't know why, but just speeding things up. The sample standard deviation. So if I was to calculate this here, this is the sample standard deviation. If you want, you can calculate it. You take the sum of each xi and subtract the mean, which is 55, and divide by n minus 1, which is going to be, what's n minus 1 in this case? 4, right? 4, good. So our degrees of freedom, so our S is equal to 3.74. You can check that. Our N is equal to 5, and our degrees of freedom is equal to 4. And we need the critical value T star on 95. So let's see what value that is. So I just wrote across the top here what we've been given. Okay, so let's write that out. And we already have it down there. I did it in the example. So 4 degrees of freedom is 2.776, right? Because I take the row. I'm going to take the degrees of freedom is right here. And I'm taking that row 4. And I go across and get the tabulation there. It's 2.776. And we go back. That's going to be 2.776. And now we just need our formula for the confidence interval. So a 95% confidence interval for the true average, that's going to be mu, average number of Smarties. Now this is a way to estimate all the Smarties boxes in the world, right? Because we took a random sample of 5 and we're going to estimate what all of it would be in the factory and everywhere else. It's going to be x bar plus or minus T star, and I'm doing this on 95, times S divided by square root n, which equals, and I just plug these values in, 55 plus or minus 2.776 times S was 3.74 divided by the square root of, what goes in there? 5, right? 5, because our n is 5. So that's going to equal 55 plus or minus. And if you work all that out, why don't we work that out? We have time. We can work that out. Try to work along with me. It's It really will help with your retention and understanding of this if you're actually writing it down, working along together. First step is write down what you've been given and match the words, sample average, match the words to the notation X bar, match the sample standard deviation, those words to S, right? You want to match what they are to the notation. N, 5 boxes of Smarties, N would be 5. Degrees of freedom is N minus 1, so that's going to be 4. And then we find our critical value. So does anyone have a margin of error? Anybody? So I have 55 plus or minus. We want the margin of error now. So what would that be? 2.776 times 3.74, divide by the square root of 5. I've put all of those metrics in. Yeah, at the back. Okay, 4.64. Son, what did you get? Perfect, good. So we have a consensus 4.64. Now, it could stay in that form, right? Estimate plus or minus the margin of error, or we can unravel it to get the full range. So if we take 55 and subtract 4.64, we will get 50.36 to 59.64. And there's no units, it's just the number, right? Number of Smarties in the box. So there's no, we're not doing weight, we're just looking at simply looking at the number of Smarties in the box. Right, so we have two answers, two ways to express the confidence range. It could be like this, or it could be like this. Do it like that. There. So a 95% confidence interval for the true average number of Smarties. Meaning this, so this means the population of all the Smartie boxes, right? Just like that. Okay. Next one, diet and exercise example. This is coming from an actual study conducted to see if men lose more weight by diet or exercise. So which one will it be? So we have 42 volunteers for a diet only group and 47 volunteers for the exercise group. And then the average weight loss for the diet group was 7.2 kilograms. And the sample standard deviation, there's our clue. It's not Z, it's going to be T, right? 3.7 kilograms, right? This means we're using T right here. And the average weight loss for the exercise only group was 4.0 kilograms and a sample standard deviation 3.9 kilograms. Constructed 95% confidence interval for the mean weight loss for each method. So let's do the diet first. And we have, so for the diet, we have X bar equals 7.2 kilograms. S is equal to 3.7 kilograms. We have N equals 42 volunteers. Degrees of freedom would be equal to 41, right? It's always N minus 1. And our critical value T star on 41 degrees of freedom, we need to go to the table to get that. So we're looking at those who were on the diet first, and then, so it's two confidence intervals, one for diet, one for exercise. Okay, so let's go over here. Now we don't have a 41 degrees of freedom, but we have a 40. So let's take 40. It's always best to round down on these things. And there's our value there that corresponds to the 95. 2.021, right? Because it's in the 95% column. These were 95% confidence intervals, correct? The question asked for 95. Yep, so 95 would be this column on 40 degrees of freedom, gives us that T. 2.021. Whoop. So 2.021, let's go back. 2.021. And then we can put this one all together. X bar plus or minus T star. We'll wait for the S, put the S in now. And that equals 7.2 plus or minus 2.021 multiplied by 3.7 divided by the square root of 42, which is going to equal that should equal 7.2 plus or minus, and what do you get for a margin of error this time? Liam? Right? 1.15? Yeah, all right. 1.15. Perfect. And then that's going to be 6.05 to 8.35 kilograms. So that's the weight loss for the diet group. Roughly 6 to 8 kilograms they lost. And by the way, this was on a 40. We can put this here in blue. We used 40 degrees of freedom. Why? Because we don't have a 41 on our table. If you were using software, you could get that 41 quite simply, right? But we don't. We're going to have a table. The table is very, very close, so it will be close enough for us to get a really good estimate for the weight loss there. So for the exercise, I'm going to do that on the next sheet. For the exercise group, we're going to have X bar equaled, this time they lost 4 kilograms. S was equal to 3.9 kilograms. And then there was, N is 47 volunteers. That makes our degrees of freedom 46. And our critical value T star on 95, we're going to use, this time we're going to still use 40 because we could use 50, but we can err on the side of caution and take the larger T. You'll notice 40 is larger than 50. And if you're kind of, with these tests, we always round down. So like even if it was 49, I would probably pick 40 because it's a little bit smaller. So this is a larger T. It's much safer to have a wider confidence interval. It's sort of erring on the conservative side. So we'll choose that 40 again, 2.021. And then this will be a good estimate. Even though there's more, we'll use 40. So we have X bar plus or minus our critical value T star times S divided by N. That's going to be equal to 4. Now we're just plugging in our metrics here. Our values 2.021 times S is 3.9 divided by the square root of, this time we divide by the square root of 47, yep. Which equals 4 plus or minus. I'll give you a moment to catch up. We can calculate what that margin of error would be. It is. Isn't that something? It works out 1.15. Very, very close, just because the numerator and the denominator, they just work out that way. So we have the same margin of error. So it's really going to all matter. It's just going to boil down to the value of the mean, right? But we'll do the full range here, 2.85 to 5.15 kilograms. And so if you compare those two, you can compare. I'm just going to shrink it down, and you can see which one was better, the diet or the exercise. Better meaning more weight loss, right? Diet or exercise? Yeah. Diet. Yes, they lost more, right? They lost between 6 and 8 kilograms, where for the exercise, it was 2 to 5. Okay, so the ones with the diet only, for this study, actually lost more. Right. So that's the mean weight loss for each group, the diet and the exercise. Yeah. It's very accurate. Yep. Because they're close enough to compare them, because do you mean for the comparison?
Yeah.
47. Correct. Yeah, but they're close enough. Now, if one group was 5 people and the other group was 50, then, or even 47, then we probably wouldn't want to compare them. But if they're close, like this is fairly close enough, then we can. It's completely safe to do that. In fact, when we get to our last chapter in the course, which is chapter 21, we're going to look at this, and we will do a 2-sample confidence interval. These are what we did here was 1 sample confidence interval. We have 2 of them here. So 1 sample confidence interval for diet, 1 for exercise. In the last chapter of the course, we do what is called a 2-sample. So we're drawing from 2 populations at the same time, and then we're going to boil it all into 1 formula. Instead of having 2 confidence intervals, we're going to have 1. And then the end of the course. That's it. Okay. Yeah. So we will revisit this again. So it's completely perfect to, it's a good question though. Can you compare groups when they're not exactly the same size? Yes, it happens all the time. Think of this done in a study, when they're studying and they're comparing, group A with group B, and they're not quite the same. It's quite often the volunteer groups won't be exactly the same. It's right. But if they're close, then it's good. All right. Any other questions about the confidence intervals? T-sample, right? T procedures. So we have the 1-sample t-test, and this is where the word comes from. So this is what the head brewmaster at Guinness was doing, the t-test, and he was conducting it. Nothing changes. It's exactly the same as how we did it with the Z. The only thing different is the S. If we don't know this, the population standard deviation, and we're using S instead, then we have to have T. And so it still has an SRS from a size N from a large population, unknown mean mu, and standard deviation. This is the test statistic right there. That's the test statistic. And then you can have the H naught. So the null hypothesis can be against case 1, case 2, or case 3, where we have these 3 different alternative hypotheses, right? We can test a greater than, we can test less than, and we can also test does not equals. 3 different ways to conduct the test. And the p-values are on that same t table. We're going to see how to get the p-values, okay, in just a moment. sort of a strange example. Anyways, I might remove this for the next time this is taught. I think we are better off with the Smarties and Tim Hortons. This one here I pulled, was a test that was actually done in Tim Hortons. I believe it was in Alberta. And so they have these new extra large coffee, and a study was done to see if the amount of coffee poured into the extra large cups differed from 710 mils. That's what it's advertised for. And of course, not everybody would pour exactly the same, but there's variability, but it should be close, right? It should be close. The cup should hold roughly what they're advertising, they're selling it at. So an SRS, simple random sample, was taken, and they measured 1, 2, 3, 4, 5 cups, right? So our N equals 5 here. There's 1, 2, 3, 4, 5. One was bang on, 710, right? One was exactly what they advertise it at. Someone had a steady hand. So this gives an average of 697 milliliters and a sample standard deviation of 19.326. And I suppose that would also be in milliliters. Test to see if the data supports Tim Hortons' claim that the mean amount of coffee poured into their extra large coffee cups is in fact 710 milliliters. And we'll use a significance level of 5%. That's alpha, right? That's our 5%. And so what I'm going to do before we go on this, I'm going to actually clear the annotations here. So we have a fresh table, and we'll put this together. Let's all work together to see what happened with this test. This was conducted. Just going to grab a darker color here. And so we have our values. The sample was 697 mils. The sample standard deviation for those, and you can work that out. You can work both of these out, right? If you add up those 5 values and divide by 5, you should get 697, because I'm giving you all the raw values. You should be able to calculate the mean from those 5 cups. Should come to 697 mils. And you can also convince yourself that the sample standard deviation is equal to 19.326 using that formula. I'll just put it here again, just to remind everybody, it's this each value. So would be 5 values, subtract the mean, right? And divide by n minus 1. In this case, it would be 5 minus 1, which is 4. And so that ends up being, in this case, equal to 19.326. So you can try it. You have the 5 raw values from the cups that were poured at the Tim's, and make sure those are good. And then we have our N equals 5 cups. That our degrees of freedom is going to be 4. And we need to get our critical value, what they used. What did they use? 95%. Or actually, what are we doing here? We're going to do the test. We're going to conduct the hypothesis test. So let's do that. Let me see. Yeah, so step 1. Let's get the null. What would you say they're testing? What do you think they did? They want to know if the true mean, true average cup of coffee is equal to, what do they sell it for? What do they sell the cups for? The new extra large cups are 710, right? So that's equal to 710 versus the alternative is going to be mu. What should we use here? Based on the words. Test to see if the data supports Tim Hortons' claim that the mean amount of coffee poured into their extra coffee cups is 710. So it's, yeah, exactly. Yes, does not equal. So we have now this time a 2-sided test two-sided t-test. It's a two-sided t-test. And by the way, I should mention, in practice, it's the t that we use. Rarely do I see a z test, like a z hypothesis test or a confidence interval. Usually we use these t's because they're more, the accuracy is just better. Yes. We used, you mean for the population standard deviation? We're still doing we're still doing, so there's two things happening, right? For Z, when we use Z, we're doing it for mu, but it's because of the sigma. It's because of that sigma there. And if you know the population standard deviation, then you don't use T. That's the difference. The T is going to be we're still estimating for mu. We're still drawing inferences on the true average, same thing, but we have this S, the sample standard deviation. Those are the differences right there. So step 2 is we're going to calculate the test statistic, which is going to be our T, which is going to be X bar, subtract mu naught, divide by S over square root n, which is, we plug those values in, it's going to be 697, subtract 710, divide by 19.326, divide by the square root of 5. So when you're plugging this in, make sure you're getting the same as what the rest of us are getting. Carefully keep brackets, keep everything in the denominator, right? So it all stays good. I don't put the brackets on when I write it, but when you're putting it into the calculator, you definitely want those brackets to keep everything so it's accurate. Does anyone have a test statistic? Perfect. I'm going to do negative 1.502. Did you say, or 4? Does anybody get 2? I had 2 from previous, but it could be wrong. Let's all do a double check. See what we all get. 697, subtract 710. Should be very close. 19.326 divide by the square root of 5. Yeah, it's 4. All right, so the third decimal is 4. Thank you for that. And it's negative. Now, because the t distribution is symmetric, we can just use the positive. So we go to the degrees of freedom, which is 4. So this is 4, right? Degrees of freedom equaled 4. And our test statistic, it wasn't a star. It was just a regular t. The t stars are what go into the confidence interval. Just the regular t is just the test statistic. And it was 1.504. Where does that fall in that row for 4? Where does it fall? Does everyone see? I'm going to bring it up here. So it falls, yeah, in between 70 and 80. Right, in between 70 and 80. So this value is somewhere between there, right? It's somewhere between 1.19 and 1.533, right? And it's because it's between 70 and 80, the two-sided confidence interval is going to be between two-sided. It's going to be between the opposite of that. So if it's between 70 and 80, the p-value is going to be between 20 and 30. It all fits. So if it's 70 and 80 here, the p-value is going to be 20 and 30 here. It's going to all add up. The two-sided p-value is 0.2 or 20%. If you add that to 80, you get 100. The other one, if the two-sided p-value is 0.3, which is 30%, if you add that to the top of the row, it's 70. It adds up to 100%. So the p-value is between, right here, it's between 20 and 30%. So let's go back and write that down. So the t, which equaled 1.504, we just ignore the negative. It was between, what were the values? 1.19 and 1.533. Let me see, 1.19 and 1.533. Okay, and that corresponded to a p-value, and this was a two-sided p-value, between 0.1, nope, between 20 and 30%. So RT of 1.504 fell on the table on 11 degrees of, how many degrees? 4 degrees of freedom. 4 degrees of freedom. We had 5 cups of coffee. So that's on 4 degrees of freedom. So our value fell between 1.19 and 1.533. The p-value then, if you scroll down, you'll see that that corresponds to 0.2 and 0.3. Or scroll up, you said it was between 70 and 80. You just take the counter of that, right? The complement of that. And then what are we going to do? Those are massive p-values. So since the p-value range is less than 5%, like it's way greater than, right? 20 and 30% is way, way bigger than 5%. What is our decision? Yeah. Perfect. We cannot reject. So if you are, so this is, and this is a good result for TIMS, right? Means they're doing it. It's good. The 710 mils hold. Yes. Oh, lots of times we reject. We did on the last chapter. Oh, yeah. Yeah. It can, you never know until you write it out. Yeah, there's lots of times we reject the null hypothesis. We just, yeah. When do we reject? If the p-value range is less than 5%, then we reject. Remember the decision rule. And that's the same as if you're doing Z or T. All those other rules, all those rules stay. They're exactly the same. If the p-value is less than 5%, then you reject. If it's greater than 5%, you cannot reject. And the 5%, what is that? That's our alpha. That's our significance level. Right? Significance level. We have another one. Another one I pulled up was the MBA programs. All right, the SRS of 20 MBA programs was taken. And we have in Canada, for each MBA program, the in-province annual tuition was recorded. The mean tuition was found to be 36,625 and a sample standard deviation of 24,645. Determine whether the in-province tuition for all MBA programs in Canada is more than 80,000. Use significance level at the 5%. That's a typo. I was just going to say that's not going to work. So there's like a sanity check that we do with these things. If your mean, if in your numerator you're subtracting like your x bar and your mean, if they're not sort of close in size, then you're doing it wrong. And so this is saying 80,000, that's so far from 36,000. It doesn't even have apples to apples. So I'm looking at my original notes and that should be a 3. So you can fix that. I don't know how that got through. My original lecture notes say 30,000. So the null hypothesis in this case is we're going to be testing that 30,000 versus an alternative. What would we do for the alternative? More. Keyword is more. So that means we're going to have more. That will be greater than, that's the more, 30,000.